Good day everyone. Today we are here to inform you about the general aspects of our project and our overall progress. Our project is to design a 6-leg parallel robot with 6 degrees of freedom, which is also known as steward platform, for our main stakeholder TAI to be used as a positioning tool in its assembly processes. Steward platform has 6 linear actuators as legs, and they are attached in pairs to 3 positions on each base plate and top plate of the platform. However, there are also many research about the number and the positioning of the legs, like the example in the left figure, which is a simpler alternative with 3 legs and 3 degrees of freedom. Steward platform is a perfect example for mechatronics because it has a relatively complex mechanical design, many electronic components such as motors and drivers, and its ability to move in 6 degrees of freedom requires a control system with precise feedback from sensors. In our researches, we have seen that steward platform designs can vary widely according to size and actuating type. Therefore, many control theories on steward platforms, mainly based around inverse kinematic solution, can be found, and there are many examples of different usages of steward platforms, from giant flight simulators to precise positioners used in assembly, which is the main purpose of our project. Assembly processes may require precise positioning, specific angle, and protection against unexpected loadings and impacts, since they can cause critical errors. Thanks to their ability to move in 6 degrees of freedom and improved control systems, steered platforms can meet all of these requirements. As we saw the example products in previous slides, steered platforms are used for positioning in other countries, but their high cost prevented them to be used in Turkey. Instead, various guides, like the example in the figure, are used, and even though they are cheaper when considered individually, their limited usage makes them more expensive in the long run. One of the most important aspects of the steered platform design is choosing the actuator type of the legs. For that, we had 3 options, which are hydraulic, pneumatic, and electric, but hydraulic option was eliminated by our stakeholder. That left us with deciding between pneumatic and electric options. When comparing the two, the only advantage of pneumatic is the higher load capacity. However, if we look at the graphs taken from a pneumatic steward platform article, the precision of pneumatic system is over 5 mm, which is way over our necessary precision set by our stakeholder, and also its cost is higher. As the final process in deciding the actuator type, we wanted to make a trade-off analysis between the 3 options in order to be sure on our decision. As we can see, electric has the obvious advantage, especially in cost, maintenance, and applicability, so we choose electric.
So, we are designing a platform that will be used in assembly processes in the defense industry. Our technical requirements are directly given by our stakeholders, TAI. System should be able to move in 400 mm in XY axis, and overall positioning precision should be up to 0.1 mm. System should hold its position against external forces and impacts, and system should be able to operate under 10 kg of external load.
Positioning of upper platform is pretty trivial. Since we know the outcome of the movement because user gave us from control panel, we can calculate endpoints of legs that connect to upper table. This movement itself per point may seem like a straight line, which can be divided to 2 parts, rotational and translational movement. User actually doesn't give us the real endpoints, it just gives us relative offsets from upper table and necessary rotational info. One way to merge this movement is first rotate all points with simple rotation matrix per axis around the origin of upper table, then translate them via given translational input. After these operations, we will have necessary leg endpoints. Since we already know leg's bottom connection points, we can calculate vector length to find leg's length. If we can limit a leg's length, force acting on it will cause its joints to rotate depending on which direction force acted. So if we just keep motors running until leg's length is reached, each leg will create a force on other 5 legs, which will cause the system to move, but not in a random position exactly where it should be.
Since precision is quite important for us, we need high precision linear actuators. Picture on the left shows a commercially available high precision linear actuator which is suitable for this project, but they are quite expensive. Since our budget is limited, we decided to design our own linear actuators. Picture on the right shows our linear actuator design. To convert the rotational motion into linear motion, we used Acme lead screw. The advantages of lead screws are they are self-locking, cheap, high precision and accuracy, low maintenance cost, simple design and easy implementation. With this screw, we can obtain theoretically 62.5 micrometers linear precision with 64 CPR encoder. With proper lubrication, Self-locking condition is satisfied while also increasing efficiency. Rise in torque is 0.17 Nm and efficiency is 30%.
For motor selection, we have three requirements. First of all, it should be able to output 0.6 Nm torque continuously. Second, it should have high precision, meaning it should either be a high precision servo or step motor or a DC motor with high CPR encoder. Lastly, the motor should be within our budget of 5,000 Turkish liras, considering other expenses. With all the requirements in mind, we decided to use a DC motor, because precise step motors, including their drivers, are not within our budget, and servo motors have to be operated in wheel mode due to our range requirements, which is basically DC motor operation, but without any form of feedback such as encoder feedback. Therefore, we decided to use both DC motor 37D series, specifically the one with 100 to 1 reduction ratio, because it is written in the datasheet that these motors should not be operated frequently, about 25% of their stall torque. Going for 70 to 1 reduction ratio would cause the motor to go over 25%, and choosing a higher reduction would just decrease RPM with no advantage. The motor's performance graph gives us our operating conditions. Drawing a line from our operating point of 0.6 Nm shows that the motor will draw around 1 amps in continuous operation. The power will be 5 watts with almost maximum efficiency of 43%, which is also one of the main reasons this motor was chosen. The speed will be roughly 82 rpm, which will give us a linear speed of around 5.2 mm per second. The stakeholders' requirement was 50 mm per second, but due to our budget we have to update this requirement.
Design. Here is an exploded view of the assembly. It includes the lead screw, nut, upper leg, spline shaft, connection parts, guide rod, motor cap and outer cover. All parts are designed considering their loading conditions and strength calculations. We analyzed two critical parts in ANSYS. Guide rod part. Since it's long and thin, it may bend with side loading. We analyzed this part with side loading. The deformation is 0.36 mm, which is acceptable. Other critical part is the motor and its cap. As you can see, the motor shaft carries all the system's load and it may cause deflection in the shaft. We analyzed this part with vertical loading. As we can see, deflection is 0.02 mm. As design progresses, we will analyze whole assembly and if needed, we will make changes in design.
The motor will be controlled using PWM signals along with motor driver. The drivers are used to isolate the high current from STM card and also because STM card cannot output such high currents. For the controller part, we will be using sensor fusion with Kalman filter. We will use a number of pulses coming from the DC motor encoder to have a predicted state estimate. Along with the data from the position sensors, we will put these two data into Kalman filter to minimize sensor error and processing noise to achieve precise position control.
We decided to use STM32F4X series embedded card. That series has its own encoder chip, relatively high clock speed, and its computer communication can be done easily via serial port. A desktop computer will be responsible for sending user input to card. After that, card will be responsible to move platform according to our control scheme.